In this problem, we have to reconstruct itinerary from a given list of flights between different cities. So you will be given a list. So let's say this city is A, this city is B, and this city is C. So you may be given a list like BA. Then you will be given a list of all the edges. So BA means flying from B to A, and these all are the flights taken by a common person, single person. But you don't know which order, so you have to construct a valid itinerary. That means it's not possible that person first flew to C, because there is no outgoing edge from C. C is just the end point or destination. You cannot go anywhere from C. So this cannot be the first flight. So first maybe either B to A or A to B. But if the first flight is B to A, then it comes to A, then either it takes C or B. In both cases, or one of the other flights will be missing. You have to cover all the edges. All are valid flights taken by a person. So the valid path would be here. Go from A to B. So the person was initially at A, then went to B, then came back to A using this line. So this is the 1, 2 and 3. Then back to A to B, B to A, and then finally C. So this should be the valid for this one. In this case we had just one valid path, but in some problems there can be multiple valid paths. In that case we will return that value which is lexicographically occurring earlier. And you are also given that the source is always a city called JFK. So these are the airport codes in 3 digits. So you have to start from JFK only. This is the starting point. So let's see how we will solve it. Clearly it's a graph problem and we are given a list of edges. So this is just one example. So these are the different flights taken by a person, and this is a valid output. So first step is to build the graph. So we will represent it in adjacency list form. So there is a flight from JFK to SFO. So JFK to SFO, there is one flight taken by this person. Then JFK to ATL. So this is another flight. This we have done. Then SFO to ATL. So there is another flight like this. Then ATL to JFK. So there is another flight like this. And then ATL to SFO. So we have constructed all the edges. Now let's see the adjacency list of each node. So these are the nodes JFK, SFO and ATL. So it's JFK, then we have ATL, and then we have SFO. So from JFK there are 2 outgoing edges, SFO and ATL, but we have to first try to traverse lexicographically earlier. So we will keep them sorted. ATL first and SFO next. In ATL there is 2 outgoing edges, JFK and SFO. So JFK and SFO. And in SFO there is just one outgoing edge, which is ATL. And we have to always start from JFK in all the problems. So this will always be one of the airports in the input. So we are starting DFS from here. Only thing is that instead of normal DFS, in normal DFS if we reach a vertex we consider it visited and we don't visit it twice. So if we came from some vertex to some other vertex, then some other vertex, and there is an edge like this, So once we reach here, we don't take this edge, since this is going to a vertex which is already visited. But in this case, the only difference is that we will not mark it as visited. Instead, we will come back here, since there may be more outgoing flights. So here the notion of visited has changed. We will not mark it as visited, but instead, to ensure that, so if we don't mark it as visited, what's the guarantee that we will not come back again? Since we take this edge again and reach here, and now we will look at its neighbors. So this will also be a neighbor, so we may again come here. So in order to get rid of that, once we move from this to this, we remove this edge. So person has taken the flight, so there is no point in taking it again. Although the person may have taken this flight from A to B multiple times, then we will have multiple edges like this. So this B will be occurring multiple times in the adjacency list of A. So every time we reach B, we delete one edge, so that we don't repeat it like in this case. So this way we are keeping track of avoiding taking one edge multiple times. So we will take each edge once. So here the notion of visited is not there. We have to take each edge once. And once we take an edge, traverse an edge, that is we come from this to this, there is no need for this. We have visited this edge. So here the notion of visited is not for nodes, but for edges. So we can mark that visited by just deleting it. So you come here, delete it. So let's begin how we will do that. So we will modify our DFS approach here. So let's start from JFK. So we will start from here, and then we go to ATL, since it's first in the adjacency list, since these are sorted. And here instead of labels from 0 to n, we have string values. So we cannot use some fixed size vector which we know beforehand, but instead we will use a map where the key will be this airport code. So a map of a string, and the second is a list or a set, and we will keep this sorted. So we can use set in C++. Set uses red black trees internally, so these will be sorted. We are not using unordered set. And in Java we can use a priority queue, or we can use a tree set or tree map, where we keep track of this string and also the count, how many times it has occurred. Or we can use simply priority queue, that will sort it based on alphabetical order of strings. So we come to JFK, we are here. Then so we call DFS of JFK. Then we look at its neighbors. So first it will be ATL. So we will come to ATL, or we will call DFS ATL, and then this edge we have taken. So let's delete this or mark this in blue. So assume that this edge does not exist now. We have come through this edge. So in actual code we will also remove this. So this ATL will go away from this adjacency list. So we pick the first neighbor and also delete it from the list. So now this JFK will have just one value. And here again we will call DFS. And at ATL we have JFK and SFO. So which one we will take? Alphabetic order. So it will call DFS of JFK and get rid of this, and we come here. And JFK again look at its other neighbors, that is it will pick the first one in the list, and now there is only one, so it will call DFS on SFO, and it takes this edge and we remove it. Now we are at SFO, so we go to SFO and see what is the first neighbor, which is ATL. So it will come here, it will call DFS on ATL, and we get rid of this. Then we come to ATL, we see what is the neighbor, so only SFO is remaining. So we will take this edge, go to SFO and delete it. So you can see DFS getting called for same node multiple times, and here we are considering edges as visited. Now we come back to SFO and we look at its neighbors. There are no neighbors, so that means we are done with this. So when we are done with this, we insert it into a stack. So let's write the code first, then we will run through, complete that example. So create itinerary, and we are given edge list here. So first build adjacency list. This will be a map where key will be the airport code or a string, and this will be a set, or rather multi-set, since there can be multiple edges like this, multiple flights from A to B in the same direction as well. So build the adjacency list based on the edge list that is given to us, just like we built it here manually. So JFK SFO means in JFK insert SFO, in JFK insert ATL, in SFO insert ATL, and so on. This way we will build this adjacency list. This is the first step, and once we have built this, we will start doing DFS, and we have to do DFS from a particular airport, which is JFK. This is always the starting node. And in DFS function, if so till we have some node in this adjacency list of S, ADJ of S is not empty, then what we do, we pick ADJ S dot front, that is the first neighbor, and we do DFS on this. And finally this, when this becomes empty, that means there is no way to go from this node. And when this will become empty, so whenever we take an edge, we delete it, and we delete this once from this its neighbors list. So finally it will become empty when we have taken all the outgoing edges. So when this becomes empty, we will insert this S to the stack. Push S. And finally we will take one element at a time from the top and print it or return in the result. So let's complete this example. So we had completed at SFO, so we had inserted SFO there. Then this call of ATL would terminate. So this call terminates here. So ATL is printed, inserted into the stack. Then this terminates back to SFO. And this call terminates here. So JFK will be inserted. And this call again terminates here. So ATL will be inserted. And this call terminates here. So JFK will be inserted. So from where we have started, that will be the final node in the stack, that is at the top of the stack. So let's write the path. It simply keep popping one element at a time. So JFK is popped, then we go to ATL, then we go to JFK, then we go to SFO, then ATL, and finally SFO. And let's match if it matches our answer. So JFK, ATL, JFK, ATL, JFK, SFO, then ATL, SFO. So this is a valid path. There can be other solution as well. From JFK we can go to SFO, and from SFO to ATL, and then again JFK, and then ATL, and then SFO. That will also work, but we will take this whichever is lexicographically first. So this one will be the correct answer here. Let's take one more example. Let's say we have JFK, and then we have, let's say, XYZ, and back here, and then YXZ, like this. So again we will start from JFK. So DFS of JFK, it will take this path since this is smaller x. So it takes this path. So it calls DFS XYG, and then this takes this path and calls DFS of JFK, and this calls YXG, and now this one has no other neighbor, so this vertex is done. So this DFS call terminates, and we put it into the stack, that is YXZ, then this terminates here, JFK, then XYG, and JFK. So what is the order? JFK, XYG. So JFK we are first here, then we go to XYG, then again JFK. So this is the second flight, and then finally YXG, or third flight. So this way we have to code this thing. So let's code it in C++, Java, and Python. So this is the same example. I had taken this second example since this was slightly generic. So this is our adjacency list. Here it's a map. And we will take multi-set instead of set, because we can have edges from A to B multiple times. So we have to build this. So simply ADJ, T will hold two values. So in T0 insert T1. And that's it. This will build the adjacency list. Then let's create this result. And then we will call DFS on JFK. Let's make it private. And it needs this adjacency list. We can also make it member of this class, or we can pass it by reference. And it also needs this result where it will populate the values. So while this is not empty, then we will pick the front. And once we have traversed all outgoing edges, we will insert it into the result. So instead of a stack, we will directly push it into our result. But we can push in the beginning or end. If we push in the beginning, we don't need to do anything. We can simply return that result. But pushing in the beginning is very costly in this vector. Everything needs to be shifted. So overall, if we insert n items, it will take n square times. First time no shift, second time one shift, third time two shifts. So 1 plus 2 plus 3 all the way up to n square. So it's better to append in the end, and finally we will reverse that. So that will be overall order n. Or you can push into a temporary stack and then finally pop one by one and keep inserting into the result. Both are same things. So here we will reverse it. So let's submit, and the solution is accepted, and it's right here around 78% of the submissions. Now let's do this in Java. So in Java you can use there is no multi-set, so either we can have a tree set and also tree map, and where we will have string and also a count. So if we have multiple times, we will increment the count, and while we want to remove, we will decrement the count. And when count becomes 0, either we remove it or we devise our code in such a way that its count is more than 0. So it's better to use priority queue here. That would be much simpler. So let's first copy DFS. So key of the map remains same, string, and here instead of multi-queue we will have priority queue. Priority QUEUE. Here we need to check if it's absent, then we need to create a new priority queue for corresponding to that. node when we are inserting a neighbor to the first time. So adj dot put if absent this is the first one, is the source that will be the key for this adjacency list, since we are adding it for the first time. And new so T0 means so adjacency list is built and our result is list of a string. So here we cannot directly check like this. If this is absent, then this will throw an error. So let's save it. String pq. Not empty. Here it's a linked list, so we can directly add in the beginning. In the C++ we had not added in the beginning since that was costly for vectors. So here we will not need this reverse. And the Java solution is also accepted. And we are right here around 100% mark. Finally, we will do it in Python 3. and here we will sort the tickets. So that's why whenever we are creating our adjacency list, already we will add the one which comes early in lexicographically first. So let's sort it beforehand. And we will sort based on second thing. If there is an edge from U to V, we will sort based on V, because that is what we are adding as a neighbor of the first. If U has already been inserted, a key has already been created corresponding to U, then we will simply append it. If not, then we will create it and then add a value there. And we start DFS from JFK, and here also we are appending in the end, and we need to reverse it. Line 16. First neighbor. And the Python code is also accepted.